Welcome to today's webinar. Today we're going to focus on features you might have missed in ITASCA software with our new point releases. A reminder, version 9.0 is the current major release version of ITASCA software. And when we moved from version 7 to version 9, there were some very significant improvements, such as much faster solution runtimes. We improved the user interface. We added something called zone joints, which are essentially UDEC and 3DEC style joints that are now available in FLAC 3D and FLAC 2D. We have also added nonlinear structural elements, so liners, cables, bolts, things like that. We added a number of new and improved some existing constitutive models. An example of a new constitutive model is the concrete model. We improved the performance of dynamic modeling, where we have very big differences in stiffnesses of materials. So where we have a soft soil or a stiffer structural element, a pile, for example. We enhanced the scripting, both Fish, ITASCA's scripting language, and Python. And then we added flexibility, both in terms of the user interface, being able to bring in your own Python libraries, and just generally working with third-party organizations. So, point releases. ITASCA software is a single installer that includes FLAC 2D, FLAC 3D, 3DEC, MassFlow, and PFC, and these all share a common user interface. Point releases offer new features and improvements that altogether will make up the next major release. Point releases also provide access to new features and improvements sooner rather than waiting for our typical 3 to 4 year major release development schedule. Point releases are only available through a subscription license or a perpetual license with the maintenance. All save and data files are compatible with version 7, 9, and other point releases. Version 9.4 is the fourth and current point release, and we are expecting and excited for version 9.5 to be released this September. Just a reminder, bug fixes and minor updates continue to be available for perpetual licenses as well as subscriptions as part of ITASCA's free technical support, as described in our EULA, the end user licensing agreement. In terms of new features and capabilities, let's focus on the user interface first. Here we have an object tree where we have now organized it a little bit differently in terms of projects. And you can see when we expand that, we see the familiar space, but now we have new tools. So we can see the file in the containing folder through Windows. So easy to find your files. If we make a new split in the workspace, we can just drag and drop different plots and create new plots in the same space. Here we're now looking at a history chart. If we looked at save states, we can get meta information about the saved file. So we can see what program it was run in, what version, how many cycles have occurred, etc. In terms of the model state, we can get information about the zones, the number of zones, and a range of data that's available. With this, we can just simply plot all that information easily in the console. And then we can also go and save that information to a file. We can look at the model, check if gravity is turned on, and where our total number of cycles run are for that model. If we look at fish values that are available, we can see we've got a fish variable called maxdis, and if we add it to the watch list, it gets put down below. So then it's outside and we can more easily track it. Looking at program settings, we can see things like our current working directory, if any logs are being recorded, and so forth. Of course, we can turn any of these sections off to make it clearer or more usable for you. So that is a quick overview of the object tree, and it really is a nice way to quickly find a lot of information about your model state, your files, and that sort of thing. Let's now talk about performance. So in terms of speed up or faster running of models, operations, for FLAC 3D and FLAC 2D, we're able to optimize and speed up things such as model restoring, clearing the memory, so model new, and also saving the model. So for example, for a 30 gigabyte test model, so a reasonably good sized model, we're looking at anywhere from 1.7 to 3 times speed improvements. So when you're working with very large files, and it can take some time to save it or restore it, it's quite nice to have this optimization. We also added cluster computing. This is an option, so there's an additional cost to it. But what this lets you do is to run large FLAC 3D models on a cluster, which is essentially a multiple number of computers or nodes connected by a fast network. There are 3 tiers that are available for 8, 16, and 32 nodes. If we look on the right-hand side, we see here that as we increase the number of nodes where the model is being spread across, we are getting a significant speed up. In a model where perhaps we had 16 nodes, we're looking at about a 14 times speed improvement. And the way this is done is essentially to take the model, here we have a dam, and to break it apart. This is all done automatically. And we can see a section here or part of the model that would live on one node in the computer. And essentially, the analysis or the calculations are done across many machines. And then in the end, everything's brought back together. And you can then review a single unified model and look at results. In terms of a practical example, here we have a large open pit model with zone joints, quite a bit of faulting going through it, and with an 8-node system, we saw a speed improvement of around 5 times faster. So if you're talking about very large models, 10, 20, 30, 40 million or more zones, you'll see significant speed improvements when using cluster computing. Static, dynamic, and factor safety analyses are all available for cluster computing. Zone joints, pore pressure, fish, and all built-in constitutive models can also be utilized. Okay, improvements to fluid flow analysis. We have endeavored to make fluid flow analysis in FLAC 2D and FLAC 3D faster and simpler. We've added essentially implicit solvers for transient and partially saturated fluid flow, and we also added a steady state solver. If we look here in this example, what we see that in version 9.0, before we added these improvements, this model takes about 42 seconds to run. Using the implicit solver and a servo, a fluid servo, it's about 10 times faster. And if we're not interested in the transient solution and we just want to go right to the steady state solution, we can use that solver, and in a fraction of a second, we have our answer. Just a little bit more detail. So with the implicit solver, the way we've set this up is there's a fluid servo. So the analysis starts off as being an explicit solution, and then essentially where we try to make the time step as small as, or as large as possible, I should say. In this servo, because depending on the performance of the model, we may be going back and forth in terms of the size of the time step to ensure numerical stability. So this is all automatic with that command, servo on. In terms of simplification, we've endeavored to make the commands simpler and consistent. So turning fluid and mechanical on or off is not necessary anymore. These are now part of the solve commands. We also added soil saturation suction models, so in order to simulate negative pore pressures for suction. In terms of 3DAC, we added the implicit fluid flow logic in 3DAC joints and are seeing up to 30 times faster solutions. It is all possible to do fluid flow analysis in 3DAC for zoned griddle meshes. So these are models that you have essentially created a grid for through Rhino and Griddle. Next, we'll talk about coupled processes, so mechanical, fluid, thermal, etc. We updated the solve commands. So it's set up so that it solves just that process without having to worry about setting other processes on or off. Sometimes this could get a bit convoluted, especially through the data file, and now everything is greatly simplified. So solve static, solve fluid, solve thermal, solve dynamic, solve creep, and then we can get a little bit more complex and have combinations. So we can do solve fluid coupled or solve thermal coupled for a thermal analysis. And this sets up loosely coupled solves with fluid thermal as the leader and mechanical solutions as the follower. There's also a solve fluid decoupled, which solves a decoupled fluid mechanical problem. So we feel that it's easier to learn, and the idea is to lead users gradually from the simplest model to more complicated ones. These have full save and data file backwards compatibility, although there has been some commands that have been deprecated. They're still there, they're just not documented. So if you're used to doing it the way you would have done in the past, that is still completely possible. All right, Sketch Tool. So Sketch Tool is a model building tool that we have in FLAC 2D and FLAC 3D that lets you draw essentially a 2D slice of the model. In FLAC 3D, of course, you can extrude that. In this example, we'll focus on FLAC 2D. So what we're going to do is create a new sketch set called Demo. And then we're going to use an existing wizard called the Slope Wizard. But we recently added an open pit wizard to this set of tools. Zoom out a little bit. We can see a couple sections of an open pit. Now we're going to use the pre-existing tunnel wizard to add a tunnel positioned at 6525. See that there. And now the main focus we'd like to look at is essentially these joint set, fracture, and Voronoi block wizards. So the joint set generator is very much based on the UDEC tool that does the same thing. We can select the polygons and then specify a number of different parameters, including things like the angle of joint set 1, the trace length, gap, and spacing. And the nice thing is we can preview that. Now we're going to add a second joint set. Again, specify the angle, trace length, gap length, and spacing. We can preview that. Now that looks a little off. So the nice thing about the previewer is we can go back and adjust and preview again. course, once we had something that we were happy with, we would go OK, and those zone joints would be, or the geometry for those zone joints would be available. Going to cancel that. Going to go on to the next one. We're going to look at the DFN generator or fracture wizard. Again, we can set a number of different parameters. We'll take a preview there. This is based on a fracture count of 10. So let's play with that number. Now we're going to say a fracture count of 25, and now 50. There are a lot of other parameters and statistics that you can play with in order to get a DFN that is desirable. Cancel that. Let's look at the Voronoi block wizard. In this case, we're going to use a minimum length of 5, and you can see the Voronoi pattern that's being generated. If we look back at this Voronoi generation, what we're essentially looking at here is a representation of the rock mass as blocks of rock, just like we might do in a U-deck model or a 3-deck model. This essentially allows us to do things in the continuum code that we normally would be limited to in our hybrid codes, which are a combination of continuum and discrete element method, so U-deck, 3-deck. So by representing the rock mass as a series of Voronois, what we can do is specify different properties along the edges of those blocks, if you will, and then we can zone them as well, and then have a different set of properties in the zoned material. In this way, we can initiate fractures and grow fractures in this type of material. This is essentially what we would refer to in U-deck or 3-deck as a bonded block model. Okay, next let's look at new constitutive and joint models in ITASCA software. We have added for FAC 2D, FAC 3D, and 3-deck the curved Morcula model. The traditional linear Morcula model is a simplification over a limited stress range, whereas the curved Morcula model provides a complete analysis for slope stability, factor safety analysis. And what we see here is that the Morcula model, in this case for a slope, tends to overestimate the factor of safety, whereas with the curved Morcula model, we feel we're getting more accurate representation of the behavior of the material and therefore of what the actual factor of safety is. So we see a significant difference between 1.58 and 1.18 in this case. More recently, we've added the clay and soil model. This is a constitutive model that's applicable to both clay and sands. It's suitable for the assessment of static liquefaction potential and is primarily used to model mine tailings. One of the really nice things about the clay and soil model is that a relatively small set of material parameters, most of which can be calibrated from standard lab tests, is all that's needed. And then we have updated some of the examples to include this constitutive model. Here we see a tailings dam. For 3-deck, we have added a velocity weakening joint model. This essentially simulates the behavior of joints that exhibit velocity-dependent weakening. It's useful for capturing the dynamic response of rock joints, where the shear stress decreases with increasing slip velocity. And so we can see that here. Essentially, we have our friction coefficient, which is decreasing with an increase in shear velocity. This can be important for modeling seismic or fault slip, seismic rupture, or other rapid shear processes. Next, let's talk about some of the improved plotting and interpretation tools that are available. We have added bar charts for 1D structural elements to FLAC 2D. It's also available in FLAC 3D and 3DEC and PFC, wherever we have 1D structural elements. These are things like cables, bolts, beams. And essentially, rather than contouring on the edges of these structural elements, we're able to project a bar chart. It's a little easier to visualize, we feel. And you can simply select the checkbox bar on the plot item for these 1D type of structural elements. In this case, it's a beam. And then we can see it on the right-hand side for cables. We have added moment thrust diagrams to the software that has structural elements, really FLAC 2D, FLAC 3D, 3DEC, and PFC. For FLAC 2D, we have added contour lines, essentially these darker lines that are differentiating between the different contoured regions. And we've also added the ability to include labels so that we can see what those values represent. On the left-hand side, we can see new grid point coloring. So we're able to essentially view on a grid point level things such as fixities, in this case, pore pressure fixity, and just helps you get an easier visualization of what is going on in your model, what you've set it to be. And then, of course, these can be contoured. So in the bottom one, we're looking at grid point displacements by magnitude. And so rather than looking at the zone level, we're able to look at the grid point level and do this sort of contouring. In the plot item, or the plot that you may have, if you have structural elements, 1D structural elements, again, beams, cables, that sort of thing, you can right-click in the plot and export 1D structural elements. And you can do that for only those that are selected. So if you want to have a subset of structural elements, or you can do that for all the visual structural elements in the system, then you're able to export that sort of information that we're looking visually. We're able to export that to tables. And so we can see in an XY chart what the axial force is, in this case, along the length of the cable. And then, of course, that's something that could be easily exported. Okay, rapid tools. So we currently have 3 rapid tools. If you go under the main drop-down menu, and you can see rapid tools, we currently have a rock slope tool, a cable pull tool, and a hook brown calculator tool. In this demo, we're going to look at the rock slope example. The cable pull rapid tool essentially lets you calibrate numeric structural elements, cables to field or laboratory testing, and then essentially see what those properties would be based on calibrated model runs, and then easily generate the commands and values necessary to represent those cables. Hook Brown is essentially a Hook Brown calculator, so you can specify GSI and MI and UCS and all normal sorts of things that you would do when calculating Hook Brown parameters. And then once you have your calculation, you're able to essentially save that as a command so that all your constitutive model specifying Hook Brown and all the properties are essentially predefined, and you can just copy and paste that into your data file. It's also very well referenced, so you can see exactly where those calculations are coming from and the references that we're using. So in this demo for the rock slope, essentially what we have here is a tool that we're able to interact with for this simple slope. It's a hook brown material. And as we adjust things such as the dimensions of the slope, its angle, the location of the water table, we can see how that all affects a factor of safety. We can do the same thing with disturbance factor. Where these results are coming from is essentially through machine learning. So rather than building this model and running it and getting a single result, we've already essentially pre-run all the model combinations statistically within the range of the parameters that you can see here. So in this case, I believe it was thousands of models that were run in FACT 2D. And then what you can do is actually export a data file that will build that model with all those, with the set of properties based on the last set of parameters that you had specified. So you could test that against the machine learning data set, or you can modify it or add parameters that perhaps extend outside of that, or add to it to make it a more rich, complex model. So we're really excited about the integration of machine learning tools based on essentially surrogate models. So running hundreds, thousands of FACT 2D, FACT 3D, other ITASCA software models in order to build up that data set. And so we can then quite easily, after the fact, interact and get results very, very quickly. It's also a great way to learn or try to understand some of the mechanisms that's going on, that if you adjust this and something else, how are those perhaps interacting, those parameters, those factors interacting? And it's just kind of interesting to play with it and get a better understanding perhaps of what's going on. Okay, so we've added a bunch of new and updated some existing examples, mostly for FACT 2D and FACT 3D. You can see there's quite a number of examples, especially for 2D. This includes things like tunneling through a fractured rock using Voronoi, so that sort of example that we looked at earlier, deformations caused by filling of a caisson, and a number of consolidation examples. Okay, and of course there's always more. We've added a number of new functionalities for Python. Of course, in ITASCA software, there's always fish, but more and more Python is being used. So we're always expanding Python's access to the data structures available within the software, ITASCA software. So for example, we have made geometries accessible to Python. Geometries are essentially start off as CAD files, or you can build them from scratch within the software. These things are quite often used for range logic. So maybe we want to identify all of the zones below some topographical surface or bedding layer. Perhaps we want to know all the zones or blocks that are within 10 meters of some fault that's been imported from a CAD file, or all of the particles that fall within a tunnel or a stope that we can represent through geometry. We have the ability now to skip Python, fish, or tables on reset. So this is useful when we want to automate running dozens, hundreds, thousands of models, so that we don't end up clearing everything from memory as we go on from one model run to another. Also, zone field data was connected to Python. Zone field data essentially allows us to interpolate a number of different results, displacement, stresses, pore pressures, anywhere through the model. And that can also be useful for plotting results on things like geometries. If we import underground tunnels in a large scale model, we could conjure results onto those geometries using zone field data. So we've also made some improvements to one of our other software codes called MassFlow, which is a gravity flow simulator primarily used in cave mining. What we see here on the right in the video is a single draw point where material is being pulled, is being mined, and then we can see essentially the way that the rock is bulking, is moving and flowing towards that draw point. And this sort of ellipsoid shape is very typical. Of course, for an actual mine simulation, you would have hundreds of such draw points, and they'd all be being drawn at different rates, and they would be interacting possibly. So we can now track block model properties such as mineral grades and other rock properties during caving. There are over 10 new fish functions to provide more flexibility for cave analysis. We've greatly improved the draw period file import. It used to take somewhere around 10 hours in version 9.0 for a very large mining simulation, and now it just takes a few seconds. And now we're also able to model gravitational flow of rock outside of the cave propagation zone and keep track that. Okay, next, for those who don't know, we have this, I think, amazing AI tool called GeoBot. Essentially, it's an artificial intelligence assistant that's being trained on our software documentation, information that's available on the ITASCA forum, and a number of fish functions that are being supplied by ITASCA engineers. GeoBot, I should note, is publicly accessible, so you don't actually need a point release version for this. You can access it through help on either 9.0 or the latest 9.4 subscription point release. And of course, there's a website that it goes to, and it's also available through the itascasoftware.com website. There's a little widget in the bottom right-hand corner that you can click and access. So here's an example of GeoBot in action. It can understand up to 95 languages. In this case, I've asked it, how do you add cable bolts to FLAC 3D? And it's essentially gone through all that information it's being trained on, and it's giving you a step-by-step process in general, some of the important commands, and then an example. And then additional resources that you can link to get more information or details about the commands and the keywords or the background information. So again, it is an AI, so it's not 100% perfect, but I've been really impressed with the quality of answers that you get and the range of topics that it can cover. So it's really good, especially if you're new to ITASCA software, or if you just need a refresher of a command and a little bit more background information. Okay, and then I'm just going to wrap up with some teasers of what's next. With the 9.5 point release, which we're planning to have out in September, ITASCA is introducing practical rock blasting tools to our software. These tools are backed by rigorous fundamentals in rock mechanics, explosive physics, and ITASCA's modeling and consulting experience. We are planning to have a JWL constitutive model with predefined materials for typical ANFO, emulsion, and decoupled cartridge explosives. New rapid tools, including a fragmentation and vibration analysis tool, the ability to track and visualize peak particle velocities, and new blasting examples for fracture propagation, wall damage, mine scale vibrations, and more. And again, we expect to have that out next month. Okay, and then we'll just wrap up. We have some time for our questions and answers. So please, as I mentioned earlier, if you just click on the Q&A icon at the top of the Teams tool, then you can just type in your question and submit it, and then we will respond either directly, or if we need to follow up with something, we'll do that through email. Just a reminder that this webinar will be posted to ITASCA's software YouTube channel, and if you're interested in a free, fully functional 2-week trial of any ITASCA software, please let us know. Just contact us at the email there, or go to the itascasoftware.com website, and there's a contact us form that you can fill out as well. All right. Thank you very much for your attention. If anyone has any questions, we'll look at those now. Thank you.